Hello to all of you math inclined people. One of my subscribers asked me to solve one GRE problem. But before I show you the solution, I want to discuss one important mathematical concept. About the following formula. The inverse of a sequence of actions is equal to the sequence of inverse actions, but in inverse order. I want to visualize this using the Cambridge hill, which is behind me. First, I'm going to climb the Cambridge hill, action X. Then I want to have a seat, but before this I take out a newspaper to sit on, action Y. Finally, I sit down, action Z. Now I want to come back, so I will invert X, Y, Z, step by step. First, I stand up, action inverse of Z. Then I put back my newspaper, action inverse of Y. And finally, I go down from the top, action inverse of X. I perform the composition inverse of Z, inverse of Y, inverse of X, the inverse actions in inverse order, and the number of actions doesn't really matter. In this problem, they ask to express the inverse of Z. Well, if it's something we have to do, then let's do it. For this, we should invert the product of all these four multipliers. According to the theorem we have already discussed, we should invert these multipliers and put them in reverse order. So, y cubed gives us y to the negative third power, x cubed gives us x to the negative third power, then the inverse of y, and finally x to the negative 2 power gives us x squared. Of course, here we are using the formula that's discussed in another video. Two operations, raising to the power and inversion, can be done in any order. You can first raise x to the power of n and then invert it, or vice versa. First invert x and then raise to the power. This is precisely how the negative power of an element is defined in group theory. It's an important formula which derives from the associative law and which we are going to use actively here. We've completed the first task. They asked us to express, so we expressed. What's next? The second task is to put this expression in the simplest form. You can see we have four multipliers, while each answer contains only two. At least they are presented as a product of two factors. To understand what the further steps are, we should set a goal. So, our goal is to obtain the answer in the form of a product of some power of x and some power of y. It could be x to some power, y to some power, or y to some power, x to some power. These are not necessarily the same, because x, y, and their powers do not necessarily commute. So, we should reduce the number of multipliers from 4 to 2. From this point, such problems cause difficulties. We have a lot of constraints, namely 3, and we don't know exactly where to start. The expression x squared in terms of y, some information about the order of y, and some information about the relation between x and y, called conjugation. Lots of stuff. For example, we can start with x squared and replace it with y cubed. Or we can take y to the negative third, which resembles y cubed, and express this power in terms of x. Or we can express the inverse of y using this equality. After each such substitution, the number of possible options increase immediately. In many tricky mathematical solutions of non-trivial problems, you can observe certain mathematical chaos, which somehow suddenly results in the answer. Some mathematicians claim that this is a form of art, but if we are honest, they play cunning. Because usually every step is part of a hidden algorithm supported by one or several notions. So, one aim of this video is not to demonstrate the shortest solution. Maybe you can find a shorter one, but to substantiate every step as part of an algorithm. The first step has already been made. It was application of the formula to invert our product. Our goal helps us to make the second step. We really want to reduce the number of multipliers. So, let's start, for example, with the first one. You might ask, why not the last one? We'll get back to this later. Using the orange formula and this equality, we can invert it and express y to the negative third as x to the negative 2. This part, x to the negative third, y to the negative 1, x squared, remains. But x to the negative 2 and x to the negative third gives x to the negative 5 according to associativity. Note that we have replaced 4 factors with 3. What next? We can continue the idea of substitution. Let's consider x squared. You will see why it doesn't work and why we didn't choose it in the beginning. So, we will take the purple path, and after simplifications we finally obtain. Indeed, we've obtained the right form of the expression, but you can check that it doesn't coincide with any of the answers, at least at first sight. For now, we will consider this path a dead end. But using the fact that this problem is a test one, we can just use back solving and simply check every answer. Let's check if option A works, then if option B works, C as well, etc. Write a comment below if you manage to find the answer this way. Let's choose another path, a blue one. Of course, we could work with x to the negative 5, but there is a problem. Minus 5 is an odd number, but in the statement we have 2 an even power of x. We can raise the equality to the power of n, which can be either positive or negative. As a result, we can get an even power of x, which couldn't be equal to minus 5, so it doesn't work. We are left with the inverse of y, but since direct substitution doesn't reduce the number of multipliers, let's try a small transformation. Let's consider this expression. In abstract algebra, it's called the conjugation of y. We could try to separate this conjugation structure in our expression, if not precisely, then at least something very similar. So, what do we need? We want to see the inverse of y with the inverse of x to the left and x to the right. To make the equality true, we add x to the negative 4 on the left, which together with the inverse of x makes x to the negative 5, and another x on the right, which together with the first x makes x squared. And now we finally see some expression which is similar to the conjugate of y. It turns out that conjugation of an element has one useful property. If we raise this to the power of n, we can just raise the center y to this power. It means we can obtain the following expression. By the way, I visualized this property in another video. Since it works for all integers n, we can write it for n equal to minus 1. So, this could be replaced with y. In fact, the last equality could be obtained in a different way. We can invert our conjugation structure using the inversion formula. As you see, the result is the same. Finally, we obtain this expression, and we are one step away from the answer. What have we achieved? It's very similar to this expression we had before, but the one important difference is that now we have even power where we need it. From this we derive x to the negative 4. And y to the negative 6 comes from this equality, so it's also equal to identity. So the left multiplier is equal to identity, and finally you can see that option D is the right answer.
If the solution is clear, I have a question for you. It turns out that the second condition is not necessarily one of the discussed formula can help to understand why. Please write in comments how to do it.
Don't forget to press like or dislike button. If you don't want to miss my next video, please subscribe to my channel. And remember that your every comment is extremely appreciated.